Welcome back to Nature in Code. We're in chapter 3 and we just recently developed JavaScript code that allowed us to simulate genetic drift in the browser and then visualize the evolutionary dynamics. Now, I would like to step back a little bit in this video and maybe the next one to get a more quantitative handle on this. So what we've seen in these simulations is that whenever we have genetic drift, it seems to reduce genetic variation. So alleles get lost, alleles go to fixation, which is the same thing, right? If one allele goes to fixation, that means all the other alleles are lost, which is a substantial reduction in variation. But the other thing that we saw was that it seemed like the smaller the population size, the stronger that effect. And I just want to see if we can develop a mathematical intuition for these processes. And when I say mathematical intuition, I really mean a very simple sort of starting from first principles types of intuition. So this should be fairly straightforward. I suggest you follow me along with a pen and a piece of paper, and then you'll see it's really quite simple. So in order to capture what's going on, I'm going to define this variable or this quantity that I'm going to call capital G. And it is the opposite of variance. It is essentially the absence of variance. We can define it as the probability that if you pick two alleles randomly from the population of your two n alleles, that they're going to be the same allele, or let me use a technical term, they're going to be identical by state, which in our case, for example, with A1s and A2s just means, okay, they're both A1s or they're both A2s. And so it's the opposite of genetic variance, right? If one allele has gone to fixation and they're all just of one type, well then G equals 1, because the probability that you pick two alleles and they're the same is 1, because they're all the same allele anyways. And it's 0 if each allele is different from all the others. Now, what I would like to do is I would like to develop the mathematical relation between G, which is what we have in this generation, and then G dash, which is what we have in the next generation, because that should give us a good understanding of what's happening. Now, what is going on here between the two generations? Well, what we had before, right, was this infinitely sized gamete pool that was created by the 2n alleles, and then we would pick 2n alleles randomly to create the new population. And now this population would again create just making infinitely many copies of their alleles, and so we would again get an infinitely sized gamete pool, and we would again pick 2n alleles, and so on. Now, another way to think about this is basically, rather than invoking this concept of infinitely sized gamete pool, is to just say, well, we pick alleles, but then we replace them. So this is almost like, you know, your classical marble jar story, where you have a marble jar, okay, and in here you have 2n alleles. And now in order to generate the next generation, you're going to pick 2n alleles, and you will make a copy of them, and you will put them over here in the next generation in a new marble jar. And we do this, obviously we have to do this with replacement, right? So this is called with replacement, because otherwise we would just pick, if we would have to pick 2n alleles from this pool of 2n alleles without replacement, well, we would just pick all the alleles that are here, and we put the original one back, and then we do this 2n times. Then we are effectively recreating this process with an infinitely sized gamete pool. And now the question simply is, going back to this value of G, which is this probability that two alleles that you pick here are the same. So now we can really come to terms with how we can measure this. So in the next generation, right, as we're picking these, so here we'll have G, and in the next generation we'll have G dash. In the next generation, if we pick two alleles what is the probability that they're the same? Well, there's two ways that this could have come about. One could have been that they're actually really from the same, ancestor allele or ancestor marble, if you will. We picked the same marble twice, and then we made a copy, and obviously those two copies will be identical. They will be the same allele, identical in state, so the same type. And that happens with probability 1 over 2n, right? If there are 2n alleles, then the probability that you pick the same twice is 1 over 2n. There's another possibility that two alleles could be identical by state, and that's that they haven't actually been, that they haven't had the same ancestor, but that they just happen to be of the same type. Now I said, okay, they didn't have the same ancestor, right, which is simply 1 minus this over here, because that is the probability that we're picking the same allele. So the reverse of that, what that not happening, is 1 minus that probability. So this says, okay, they're not from the same ancestor. However, they happen to be the same type, which is of course exactly the definition of G that I had here in the beginning. Okay, I hope you can read this. This is a G. All right, so this is a very simple formula, right? Starting from first principles. What is the probability that in this process over here we pick two alleles, they're identical? Well, they were either copies from the same original allele over here, or they weren't, but they happen to be just the same type. So starting from this, we can now develop a very simple intuition. Okay, so I'm going to just scroll up here. First of all, actually, I'm not really interested in G. I'm interested in the opposite of G, right? The probability that two alleles are not the same, because that is really a measure for diversity. So I'm going to call this H. And of course, H is just 1 minus G, because this was the probability that two alleles would be the same. And this is the probability that two alleles are different. And of course, they have to add up to 1. And in the same vein, in the next generation, the same logic applies. So H dash, that's in the next generation, is going to be 1 minus G in the next generation. Okay, and I just had this formula for G dash, which was 1 over 2n plus 1 minus 1 over 2n times G. And so now I'd like to say, but what I really want is I want this H dash, right? So H dash is simply 1 minus G dash. So it's 1 minus this whole thing here. Okay, so I'm just going to write it out. So it's 1 minus this whole thing here plus 1 minus 1 over 2n times G. Okay. And because there's a minus here, I can get rid of the parentheses here, and I can just change the signs here. So this would be a minus. Okay. Now, G, I can replace that as well. So G is 1 minus H, right? Because H is 1 minus G. So I'm going to replace that here as well. I'm just going to get rid of G here and replace it with 1 minus H. And now what I can do is I can expand these two terms here and multiply them. So let me go ahead and do this. So H dash is 1 minus 1 over 2n minus, okay, let's see, what do we have here? All right, we have 1 times 1, we have 1 times minus H, so that's minus H. We have minus 1 over 2n times 1, so that's minus 1 over 2n. And we have minus 1 over 2n times minus H, oops, I'm sorry. 1 minus 1 over 2n times minus H, which is minus times minus, is plus, so plus H over 2n. And once again, these parentheses, here's minus parentheses. I can get rid of these parentheses. Okay, let me get rid of them. But now I just have to swap the symbols here. So this is going to be a plus. This is going to be a plus. And this is going to be a minus instead. All right, so now let's see what's happening here. So here we have 1 minus 1. Okay, we can get rid of that. So we can get rid of the 1 here and the minus 1. We have minus 1 over 2n plus 1 over 2n. So we can get rid of the 1 minus 2n, and we can get rid of the plus 1 over 2n. So that leaves us with this simple equation. So that's a plus h. So I can get rid of the h minus h over 2n. And now, of course, I can, that's a very simple equation, and I'm just going to pull the h out here. So then we'll have h dash, so in the next generation, is what h was before, times 1 minus 1 over 2n. And that, in fact, is a very profound equation, because it tells us so much about genetic drift. Let me just explain what I mean. So once again, the equation is the genetic variance in the next generation is 1 minus 1 over 2n times the genetic variance in this generation. What does that mean? Well, let's take a look at this term. N is our population size. So 2n is the size of our allele pool. And so that's just some positive number. So 1 over 2n is going to be something between 0 and 1. And so 1 minus this term is going to be something between 0 and 1 as well. But in any case, this term is going to be smaller than 1. It will approach 1 as n gets very large. But as n gets very small, it goes away further and further from 1, further and further towards 0. So what that really means, and this is important, right? Because that means, well, whatever age is now, in the next generation, it's going to be smaller, because you have to multiply with a value that's smaller than 1, a positive value that's smaller than 1. So right there you have it. Right there is the mathematical notation that your genetic variation is going to go down every generation. It's going to decrease every generation. So that's the first fundamental insight that we get from this simple formula. Now the second important insight that I want to demonstrate is the strength of this process. So okay, we've now established age in the next generation will be smaller than age in this generation. But how smaller? Well, again, let's look at this value here. If that value is closer to 1, then the effect will not be as strong. If that value is closer to 0, then, or just going further away from 1, then the effect will be stronger, because the reduction will be stronger. So what is that value? Well, if n is very large, as I said at the beginning, this value is close to 1, because if n is very large, then this expression here is very small, and 1 minus something that's very small is close to 1. So the effect is going to be weak. So when n is large, okay, so the effect of this reduction is going to be weak. However, if n is very small, then this number gets larger as n gets smaller, and consequently you move away from 1 towards 0, and so that term gets smaller. And because that term gets smaller, the reduction will be stronger. So if n is small, the effect is going to be very strong. And there you have essentially the mathematical demonstration of what we found previously with the simulations, namely that genetic drift always seems to reduce genetic variation, and that this effect seems to be stronger when the population sizes are small. So I hope this has brought home an important principle, which is you can come to the same conclusion with computational simulations and with mathematical reasoning. And for the longest time in the history of science, mathematical reasoning was the only option here because we didn't have computers. And even when we started having computers, those computers weren't quite fast enough to do the kinds of stochastic simulations that we've just done in the past few simulations, in the past few videos. However, nowadays you can do both, and you can do both very quickly, as we've seen previously. And I definitely wouldn't pit one against the other. It's always good to have both, both approaches, if you can do both approaches, and of course both of your approaches should agree. Otherwise, there's something wrong with the assumptions in either the simulations or the mathematical concepts. But here, I hope this gives a nice demonstration of how you can derive really fundamental insights about evolution or about nature in general, starting from very simple first principles. And then also you can implement these things with stochastic simulations in code and see what happens concretely in single simulation runs. So in the next video, I'd like to take another look at this formula, because you would think, wow, 2 major insights in this simple formula. Well, it turns out there's actually a third major insight, and I'm gonna explain what that is in the next video. So see you in the next video.